Alright, this is video 7 for Math 2210. Question we're going to talk about in this video is the following. Find the average of the function f of xy equal to x times y over the region of a square in part A versus the area of a quarter disk. So let's first recall what we mean by average of a function. So recall, average of the function f of x over a region R is given by the following. It's equal to the double integral over the region f of we're integrating f of xy with respect to the area there, and then we're going to divide that by the area of the region. Alright, so what we need to do to compute the average of the function over this square thing, we need to integrate over this region the function f that they gave us, and then we need to divide by the area of the region. So let's work on the square first. So there's two things we need to calculate. Let's do the easy one first. We know that the area of the region R in this case is just a times a, right? The area of a square is the product of its side lengths, so that will be a squared. Right? Now we need to compute this integral. So we need to integrate over the region, over the square, the function f of x, y, with respect to this area. Well, let's think about how we can set this up. Let's just make it easy and do Cartesian coordinates. Right? Then I can say this is going to be the integral of the function. Now it's x times y, right? And since we're doing Cartesian, we'll do dx dy, and now we need to think, alright, how is the function, what are the limits in the x direction? So the limits of this guy are going to be from 0 up to a, and then similarly in y, it will also be from 0 up to a. Alright, so we will do write in our limits now that we know what they are. Now it's just integration. So I'll kind of do this slowly in case you're still getting used to doing these double integrals. This, remember, we do the inner integral first and then the outer. So we will do this as the 0 to a of, let's do our inner integral, xy dx, and then integrate this whole thing with respect to y. Let me do what's in the brackets now, so I'll write that out. If I integrate with respect to x, that's going to be x squared y divided by 2, and then I put in my limits from 0 to a, and then I'll integrate that with respect to y after I've evaluated that at those limits. So this is the integral 0 to a. If I plug in everywhere I see, remember these are in terms of x here. Everywhere I see x, I put in my a, so I have a squared y over 2 minus, now I put in the 0, that's just going to be 0, of course, so. Right. So now I just, now I can compute this integral with respect to y. This is going to be equal to the integral from 0 to a of a squared y over 2 with respect to y, and we can integrate that pretty quickly. We see that that's just going to be y squared over 2 times, we have still this a squared over 2, and I need to evaluate that at those points, and I see when I put in a, I get out a squared times a squared, which is a to the 4th over 2 times 2, 4. And I put in 0, I get 0. And then we'll say equal, and then this, of course, is equal to just, that's the one part of my formula, that's the integration, but remember I still have to divide that by area. So then I'll come down here and I'll say that the average then is the answer that I got from the integration, which was a to the 4th over 4 divided by what the area of the region was. Well, it's a square, so it was just a squared. So this turns out to be, if I simplify that, a squared over 4. Alright, so there's my answer for the average of the function over the square region. Alright. Okay, now we have to worry about the quarter disk, but before we do the quarter disk, I just wanted to make a brief little remark here about something for polar coordinates. Let's go ahead and draw the region, and then I'll explain this figure over here in a moment. We are interested in finding the area of the function, or the average of the function over this little region here in R, right? And we can think of this in polar coordinates, right? We can think of it also in Cartesian, but it might be a little bit more difficult to integrate if we do it that way. So this is going to be our region here, right, where these little lines that I'm drawing out represent the radii coming out from this center point 0, 0. And let's think for a minute, if I wanted to change it from dy dx to the integration for, changing the limits there for polar coordinates, there's some changes that need to happen, right? I can't just say dx, dy goes to dr d theta. So let's think about for a moment what it is that I need to do. So we start out with the same thing that we would before if we're going to integrate. We're doing it over some region. The function they told us was x times y dA, right? So this dA part is the part that I want to just focus on for 2 minutes and just look right here at this little diagram that I have for us. We can kind of think about what it would be. So before, this dA, because it was a square, right, we were doing it in Cartesian coordinates. It didn't matter that it was a square, it was because we were in Cartesian coordinates. We just did dx dy because that represents a little tiny area in the Cartesian, right? This is maybe my dA here in Cartesian coordinates. Well, you see the picture is a little bit different in polar coordinates because this squared little rectangular area is now not quite a perfect square, right? We have this arcs coming out, right? Because of this, the way that we're doing our polar coordinates, these aren't going to be rectangles, they're going to be little rectangles in polar coordinates, right? So the area there will not be x times y or something like that. We have to think for a moment what it will be. Here though, we know that it will be, this area right here is just some change in r, but the problem is right here, as I go out further and further, theta, the change in theta gets larger and larger, right? So it's not that it's just going to be dr times d theta, because d theta is, like I said, as we go out, it gets farther apart, and that is actually a product of how far I go out and the distance between the two angles, right? So there's a little bit more to this picture. Maybe if you want, I could we could maybe discuss this in office hours or something. We could talk about why we need the r here a little bit more, but it has to do with how far I'm going out and that increasing the distance in theta, right? So dx dy here, in a similar way, that would be my area for Cartesian, but in polar coordinates it's r times dr times d theta, right? That will be the big change here. Okay? Alright, so a little spiel on polar coordinates, because this is going to be a lot easier to integrate if I look at this in polar coordinates. So let's do that. We have this region now, x and y. Now remember what happens with x and y. In polar coordinates, x is equal to r cosine theta, and y is equal to r sine theta. So I can replace that in here for my integrand, and I have, substituting these two guys in, r cosine theta times r sine theta, and then like I talked about, dA in this case is this guy, right? That's going to be r dr d theta, And now I need to put in my limits of integration. Alright, so this guy was that, and then I'm going to integrate first with respect to r. So r is going, starting from 0 here, and then it goes out to a. Right, so that will be from 0 to a will be the limits of integration in r. Excuse me. And then on the outside integration, we're looking at theta, right? But theta starts here at 0, and then it comes all the way up, wraps up to pi halves. That's the angle there that we stop at if we only want the quarter disk. So that will go from 0 up to pi halves. And then let's just simplify what we have in the inside here. Let's write it as r squared cosine theta sine theta r dr d theta. Or maybe I combine these and do r cubed, right? Not gonna hurt. We'll do that. Alright, now let's focus. Let's do the inside. We'll focus on the inside integration, and then we'll do the outer integration. This will be pi halves, and in the inner integral, 0 up to a r cubed cosine theta sine theta. But these guys were, if we're going to integrate with respect to r, it's only going to, those are going to be treated as constants. So this will go to r to the 4th over 4 cosine theta sine theta. Those are just constants with respect to r, and then we'll evaluate that from 0 to a. That is going to be equal to, I've actually done that integral, so that will be 0 to pi halves. If I shove in now a every time I see r, that will be a to the 4th over 4 cosine theta sine theta. Alright? Okay, perfect. So now there's a couple different ways you might approach doing this integration now with the thetas. I think that the best one, well, my preferred way would be to notice that there's a trig identity, right? Let's recall this trig identity here. That 2 cosine theta sine theta is equal to sine of 2 theta. So there's this little trig identity that I'm sure is in your calc book somewhere. But if we shove that in, then we can say, well, everywhere let's just write it a different way for a moment. I can divide this guy by 2, and I see everywhere I see cosine theta sine theta, I can shove in sine 2 theta over 2, just to make integration easier. So I can rewrite this then, going from 0 to pi halves, a to the 4th over 4 sine 2 theta. Right, that's this guy I'm shoving in, but that will be now over 2 times the d theta. Let me just simplify this up a little so you can see. A squared is a constant. 4 times 2, 8 is a constant. So I'll maybe just bring those outside the integration because I can. And I'm left on the inside sine of 2 theta d theta. Alright. Well, this is just a simple, maybe if you want to do u substitution, but it's a really simple integral. We can do that without thinking too much. This is going to be, let's think, sine would go to negative cosine, so that would be minus a to the 4th over 8 times cosine 2 theta, and I'll have to divide by 2 there from either the u substitution or backwards chain rule, however you like to think about that. And these guys are equal to theta there. And now I'll just shove that in to everywhere I see theta. So I have minus a to the 4th over 8 cosine 2 times pi halves is just going to be pi, so that will be cosine pi, minus, if I plug in 0 everywhere, I just get that this is going to minus a to the 4th times 8. I'm just going to factor him out so I can save myself a little bit of thinking for a minute, and this will be cosine at 0. Right. Over 2. Perfect. And then this will be minus a to the 4th over 16 Cosine of pi is -1. Cosine of 0 is 1, so it'll be -1. And then this goes to, this will be a -2 in here. Cancel with that negative. I will have a 2a to the 4th over 16, or just a to the 4th over 8. Now we have to remember, what we were interested in finding was not just this double integral over the region. Remember, we're interested in finding the average of the function. So we found, for the part B, we found the area, or the integral of the function over this region, but now we need to find the area of the region. So remember that the average is equal to the double integral of f of xy over area of the region, and we found out that this guy is a fourth over 8, and now we need to calculate the area of the region. Well, that's not too bad, right? We know that the area of the region is just going to be the area of the quarter circle, right? Well, the area of the whole circle, right, the area of a circle, if I have this being a, is pi r squared, right? Everybody knows that. In this case, it's pi a squared, right? Because our radius is a. And I only want 1/4 of that area, so let me just divide my answer here by 4. And that will give me this region right here that I'm interested in. Okay? Now I can shove that into the average equation that I'm looking at here to find the average of the function. That will be pi a squared over 4. And then if we do some simplifying here, this is what? A to the 4th divided by a squared, pi. And then I'll have a 4 up in the numerator and 8 in the denominator. Some things cancel here. I have a squared over, it will be 2 pi. Alright, so that's the average of the function over the region of a quarter disk, or the quarter circle there. And you notice that it's like 2 pi here is a little bit over 6, right? So that, compared with our other answer here of a 4, we notice it's a little bit, the answer here, if I divide by 6, is going to be a little bit smaller than dividing by 4. So kind of matches our intuition, because the area of the disk is a little bit smaller than the area of the square, with those guys lining up. All right, hopefully that helps you with your homework this week.